I request everybody to please have a seat. It gives me great pleasure to invite you to the first invited talk of the conference. The talk will be by Jian Guo on evolution of cryptanalysis, security updates on SHA-3 and AES hashing. About our speaker, Jian Guo is currently a faculty member at the Nanyang Technological University in Singapore. He's been working on symmetric key cryptography dedicatedly and has published over 40 papers with IACR since 2007. He co-designed several symmetric key primitives, including the lightweight block cipher LED, the lightweight hash function photon, and continuously provides updated security evaluations to important symmetric key designs such as SHA-2, SHA-3, and AES. He serves the research community actively as General Co-Chair of FSC 2013, Asiacrypt 2021, a member of the IACR Board of Directors since 2020, a member of the Asiacrypt Steering Committee since 2017, and a PC member of multiple IACR conferences and workshops. He has also co-founded the Asian Workshop on Symmetric Key Cryptography in 2011. Let's all welcome our speaker.
Thanks for the introduction and thanks for the invitation. It's my honor to present a talk here. So today I will present a topic on evolution of cryptanalysis, security updates on SHA-3 and AES hashing. So I have to acknowledge all my collaborators on these two topics. They are my ex-PhD supervisors, colleagues, postdoc students, and friends. So today I will try to give the talk in 5 parts. First, I will give the introduction on hash function and cryptanalysis. Then I will move to developments of cryptanalysis, followed by the security status of AES and AES hashing. Then I will summarize. So first of all, I have to emphasize that the talk is educational. So I tend to give the talk to general audience, including people outside of the symmetric key field. So it will not contain too much technical details, but to cover the most updated security status on the field. So starting with the definition of hash function. Hash function is a function mapping a bit string of arbitrary lengths to a fixed length digest. So usually we use H to denote the function and N to denote the size of digest. The core security has to offer collision resistance, preimage resistance, and second preimage resistance. Collision resistance refers to the property that it should be computationally difficult to find 2 different messages such that the digests are the same. So the key here is that there's no restriction on the selection of either message. The attacker or people who want to analyze it has the full degree of freedom to choose X and X prime. The second security is preimage resistance. So given a target T, it is computationally difficult to find a message X such that the digest of X is T. And second preimage resistance is very related to preimage resistance. Rather than the digest, the attacker is given a message. And the goal is to find another message such that the digests are the same. It has many significant applications. So for example, digital signature, we can use the hash and sign approach to generate the signature. Password storage usually comes with a sort together with the password before the hashing. Checksum, so this is used quite often for large file downloading. So to ensure you have a correct the file downloaded, usually what we do is to check the checksum against the one provided. If they are consistent, then it's very likely that the file is correctly downloaded. And message authentication codes in the way of hashing of a key and message, such as HMAC and NMAC. So SHA-3 was triggered by the broken of SHA-1 in 2005 by Chinese researcher Xiaoying Wang and her team. Then NIST organized this SHA-3 competition in 2008, October 64 submission received, 2009, July 14 selected for round 2, 2010, December 5 selected for round 3, and 2012, October, Ketchak was announced as a winner, decided by a group of people from Belgium. Actually, Jia is here. There. 3 years later, the Ketchak was formally standardized as SHA-3. It has 4 major digest sizes, 224, 256, 384, and 512. And later on, 2 extendable digest sizes are added. They are named Shake 128, and it has a very different design strategy from SHA-1 and SHA-2. It consists of 24 rounds, and the designer also proposed a Kangaroo 12 with 12 rounds. I will come back to this later. So another major instance of hashing is what we call AES hashing. So AES hashing is a hash function designed from AES. Because AES was so widely used, it will cause a marginal additional cost to implement a hash function if the AES itself is already implemented. So about AES, so it was the successor of DES, and there was the attack by Masui-san, so I think he's also here. I saw him yesterday, at least. So NIST organized this AES competition in 1998, June 15 submission received. The next year, August 5 selected for round 2. 2000, October, Rhino was announced the winner, designed by Zhong and Vincent. And the year after, it was formally standardized the AES. Supports 3 different keys, 128, 192, and 256. It uses the white chair strategy to resist differential cryptanalysis because differential cryptanalysis and linear cryptanalysis were the major cryptanalysis technique invented before AES, and it was the major threat to DES. And so the number of rounds are 10, 12, 14, respectively for the 3 different variants of keys. It can be converted to hash function by modes such as Davis-Meyer. So this is one example. So if we use the message as the key and hash the previous chaining value plus the key again, we'll get the updated chaining, and this will be the compression function. So as we know, cryptanalysis is the major energy consuming, human power consuming part in the whole symmetric key design cycle. It will take a lot of time actually lots of design parameters depends on the cryptanalysis results. So now it serves as a tool to trade off between the simplicity, efficiency, and security for designs through round numbers. Okay, so meaning that if usually the design is iterative with the similar round function repeated several times. When we have more rounds, it means we have a larger security margin, but lower efficiency. If we have lesser rounds, we will have higher efficiency, but lesser security margin. So cryptanalysis methods is try to make the best trade-off between the security and the efficiency so that we get an efficient one, yet not broken. Yeah. The major cryptanalysis method developed in the past 2 decades includes differential cryptanalysis, linear cryptanalysis, integral cryptanalysis, and meets in the middle attacks, boomerang attack, cube attack, etc. So take differential cryptanalysis as an example. The major portion of differential cryptanalysis is to find a good differential path. Good means high probability, yeah, and evolved from hand finding differential paths by hand, and people believe that the broken of SHA-1 was actually done by hand in 2005. And after that, people will write a dedicated program to search for differential passes according to their experiences. Like for lower number of rounds, what are the good ones, and try to propagate to a larger number of rounds. Starting from 2011, people started to utilize set-like solvers. From 2019, machine learning also found its application in cryptanalysis. So the problem is that, so we are given inputs output differences and the number of rounds we want to attack. Then people have to find the intermediate differences so that the overall differential probability is high or optimum. So the approaches are, before we have all the tools, is mainly about human experiences to narrow down the search space. So for example, we know for low number of rounds, 2 or 3, we know how to do it by hand. And if we are to build larger number of rounds, differential paths, we repeat them, or we try to add additional rounds on top of the shorter differential passes. Yeah. We also have the meet in the middle approach, meaning that if we have 2 shorter differential passes, we try to connect them by matching the inputs and the outputs of the 2 passes. Yeah. So that's what we have done for many years. So before we find useful tools like sets and machine learning. So in 2011, set-like solvers were introduced to cryptanalysis. One of the issues is that it's difficult to predict the solving time, meaning that the only thing we can do now is to try and see whether it gives us the results. If it doesn't, we don't know whether it's not solvable in real time or the model itself has some problem. Yeah. So either yes or no. Machine learning is similarly, so we're constrained by the practical complexity, meaning that once we have the model fixed, we have to train the model in practical time. If that model cannot be done in practical time, we cannot be sure whether the model is working or not. Yeah. So yes, both have this constraint of practical complexity. So for set-like solvers, it's hard to achieve optimality for any. So it's hard to achieve optimality for any cryptanalysis attacks, which are usually tunable by various parameters. So set-like solvers are here to help for better optimization. Here I list a simple example. So if we have a list of constraints with inequalities, and we define an objective function, either we want to minimize something or maximize something. So this is a very a simple example of MILP. We can directly input this into the MIP solver, and you'll be able to output us the optimum or suboptimal solution. So in this case, it's 1, 2, and the objective is 3, which is maximum. Yeah. So for curve analysis, we can actually convert all the constraints into inequalities like this and fit into the solver. Once the solver gives us some solution, then it means a solution to the curve analysis results. Yeah? So for example, the differential path search, the constraints are simply we have to make sure the differences, intermediate differences are compatible in each round. So they form a complete and compatible differential path. And the optimal goal is the overall probability, which is dependent on the choices of the intermediate differences. Okay. With quantum computer in light, we also consider the curve analysis under quantum setting. There are two major algorithms available, which are different from the classical ones. So the Grover algorithm, which is also called the quantum search algorithm, it takes the square root n time versus n in the classical computer to do the brute force search. Yeah. So the immediate impact of this is that the security strength of block ciphers is halved. So 128-bit key becomes insufficient because 2 to the 64 is very close to practical time. And second, preimage and preimage resistance of hash function is also halved, yeah, because of this brute force search. Another algorithm useful for us is the Simon's algorithm. So if the function f is periodic, means that fx is fx plus p for all x in the domain. So it costs polynomial time to find the period p. Yeah. So the immediate application of the Grover algorithm is application to quantum collision finding. So traditionally, quantum attack in classical setting, you will cost birthday time, which is square roots of the search space. Yeah. And this can be done simply by selecting 2 to the power of n different values and store the digest in the hash table, and roughly with a probability about half, we'll be able to find the repeated digest. We do the same for quantum setting, except that now we only need to store 2 to the n over 3 because now the search is done by Grover, which can be done in square roots of the search space. So if you have 2 to the n over 3 values available in the space, and the entire space is 2 to the n, the ratio will be 2 to the 2n over 3, and the time to do a search in this ratio is simply 2 to the n over 2 n over 3. Yeah. So the overall time complexity for collision finding in quantum setting is 2 to the n over 3. So it means that if the digest size is 128 bits, it only offers 2 to the 42.7 security, which is insufficient. Yeah. Another impact on differential-based collision attack is that the lowest useful probability changes from 2 to the n over 2 from the classical setting to 2 to the negative 2n over 3 in the quantum setting. Yeah, because with this probability, we only need to do the search in time 2 to the n over 3 in order to find one colliding pair. So in quantum setting, there are potentially much larger search space, and also potentially result in longer attack rounds. Yeah. So with all this in mind, meaning that with the development of the curve analysis method from the traditional ones to the solver added ones, and in the setting of classical and quantum, we'll look at the security of SHA-3 and AES hashing. So SHA-3 was following the sponge construction. the design is simple. So the internal function is a permutation f, and it starts with an initial value. So top part R bits is called rate. At each iteration, R bits of a message is added to the states at the beginning, and this was fed into the permutation f, and this was repeated until all the message bits was processed. Then it goes to the squeezing phase, which outputs R bits at each iteration until you get sufficient many bits needed. So SHA-3, there are four major instances, but they share the same permutation f, meaning that the only difference between the four instances are the parameters R and C. Yeah. It can be organized in a cube, 5 times 5 times 64 cube. It has 24 rounds. Each round consists of 5 steps, and out of the 5, there are only one nonlinear operation. The first step is called theta, which adds the parity of 2 columns into the current bits. So there was the notation of a column parity kernel, means that if all the parity of the columns are 0, then this forms in the CP kernel, and it has some special property because in this case, theta becomes the identity. Yeah, means it does nothing. And so we have the row, which is the lane level rotation. So we have 5 by 5, 25 rows, and each row rotates by a different value of offset according to this table. Pi step is the permutation of the lanes according to this formula. So meaning that we just shuffle the position of the lanes. And chi is the only non-linear operation, which is a simple circuit design, actually. We have a value here. It goes through the negation, and together with the next value, go to the AND operation and add this value as reserve, so that it updates the speeds. So this applies to every bit. We can easily see that the edge break degree of chi is 2, because there's only one non-gate, and the inverse it has edge break degree 3, which is very low compared to AES. Yota is adding a constant, round dependent constant to the state. So this is to destroy the symmetry. So overall, we can see that the Yota destroy the symmetry, and it does nothing else. So in our differential attack, we can simply ignore this one. The first 3 are linear operations, and the chi is the nonlinear part. So we can actually combine the first 3 operations to form a big linear operation. The overall attack framework is something look like this. So there are 2 So this portion actually tries to connect the initial value to the input difference here. So we call it connector. So the parts we can control is the rates because the message is added here. So we can choose the correct the message we wanted to change the value to what we want freely. But this portion capacity is fixed to 0. So there's no way for us to change it. So the value is 0. The difference is also 0. So there's nothing we can do here. So we only have the degree of freedom of this R bits. Try to connect it to the delta in here after a few rounds. So there's a series of developments work on this. In FSC 2013, the connector was 1 round. And in Asiacrypt 2017, we tried to expand it to 2 rounds by having a fully linearized rounds. Means that here we will have a layer of all S boxes active and try to linearize it. Linearize it means that we try to fix some values of the S box so that the S box becomes a linear operation. Yeah. And at Crypto 2017, we extended this to a partial 3-round connector. Means that we cannot fully control all the differences, but part of them we can do, so that we leave some of them to be probabilistic matching this data as seen, and the rest are by the connector. Yeah. Okay, so the result was at the very beginning, only 3 rounds SHA-3 512 and 4 rounds SHA-3 384 can be done, and only 3 round version SHA-3 512 can be done practically. In 2017, we extended this to 5 rounds practical attacks on Shake 128 and SHA-3 224. And later in a journal version of this paper, of these 2 papers, we also extended the practical SHA-3 256 collision result to be practical. Yeah. Yeah. So that's the original idea without the sets. Okay. So as we can see here, we actually involve 3 parts of the attack. The first part is to come up with a good differential path with high probability. The second part is to come up with the connector, which also offers sufficient number of solutions for this differential part. And the overall goal is to have an optimum complexity. So 3 parts are done independently before, and they were searched by dedicated programs. And so we can see each part can be replaced by a set-like solver. Yeah. So we did that and combine all these steps together to achieve global optimum. So what we got to are 6 rounds attacks in quantum and classical setting. So my colleague Gordon will present this paper. I think that this is the last talk of today on this portion, how this was done. Right. So that's about SHA-3. So on AES, there are 10, 12, 14 rounds of AES respectively for 3 different key instances. And the round function looks like this. It consists of 4 operations. First is the sub-byte, which replaces each byte by the substitution of S box of its value, followed by the shift row. So you shift left cyclically by 0, 1, 2, and 3 positions. Mixed column operates on the columns. So you multiply MDS matrix with the column and update it. And finally, we have the add key, so which is the round key. And this is the key schedule for AES 128. Okay. So the major collision attack on AES hashing is by the rebound attack. It also involves the high probability differentials. Yeah. So the idea is that if we have two high probability differential, we can chop the entire cipher into 3 portions. So the first one is what we call FBW, backwards. And the last portion is FW, forward, and the middle portion. So what we want is that the probability falls in this the first and last portion are high, so that when it comes to the brute force search stage, it will cost less time, and we want the FIN to connect these 2 portions and offer enough number of candidates for the brute force stage. Yeah, and this rebound attack was introduced in FSC 2009 by Mendel et al. And the first application was to WIPO and Lane. Actually, Lane was removed by this attack. Yeah. And it relies on high probability differentials of these 2 portions. So you can see that where the set-like solvers come to play. The constraint is simply the middle have to match in the state and key if in use through the FIN portion. And the overall goal for optimization is the overall complexity, means that the overall, which is highly determined by the probability of the first and last portion. Yeah? So the collision attack on AES hashing in the classical setting is reaching 7 rounds with complexity 2 to the 56. So in order for us to have collision, first of all, it has to satisfy the condition that the input difference and the output difference is possible to cancel each other. Yeah, so you can see the pattern in data B and the pattern in data C are the same. Only then it will be possible to generate collision. And then the dotted line is what we have for FIN, the middle portion. Yeah, the middle portion. We should be able to solve it by utilizing the degree of freedom from the key. Yeah, and out of that, the first 2.5 rounds is the FIN. Yeah, so in the real attack, after the inbound phase, he actually propagates backwards in this way. So the probability we are calculating here is simply, we have a mixed column of 4 to 1 here. So here is 1 to 4, that's with probability 1. So we don't pay anything. So it's just here, 4 to 1. Similarly, the last round, we have this for free because there's no more mixed column. Yeah. So the only probability we have to pay is here, and the price that this and this has to match. Yeah. So we have 3 bytes condition here and 4 bytes condition here. So in total, 7 byte condition, which is 2 to the 56. Yeah. This was not possible using the original method because previously the 2 steps were done also independently, meaning that the high probability differential of the forward and backward portion are searched independently. and the matching was done in the second step. So although each step you might reach the optimum, but globally may not be the optimum. Yeah. So after we actually consider the two steps in one and put them into one solver, so then be able to give us this new results together with the triangulation algorithm. And in the quantum setting, as I mentioned, in the quantum setting for collision, we can go for the probability as low as 2 to the 2n/3. We are able to extend this attack to 8 rounds. So again, in order for us to have collision, we have to ensure that the pattern, which is 8 bytes active here, and outputs are the same. Yeah, so they are possible to cancel each other, and we are able to solve a very big inbound space, which covers 5 rounds here. So from here to here, we cost nothing because it is 1 to 4. Yeah, and from here to here, we cost nothing because it is 1 to 4. Yeah. So in the end, the only price we have to pay is this one matching this one. Yeah. And it costs 2 to the 34 in quantum setting. So we can see in quantum setting, this is a very low complexity. So if quantum computer comes to reality, this might be the first targets we can actually implement and carry out the finding. So overall, for AES hashing, classically, we can reach 7 rounds, and in quantum setting, we can reach 8 rounds. In total, there are 10 rounds, so the security margin is becoming small. Yeah. So in summary, we've seen some developments of cryptanalysis method from the traditional methods to the ones by dedicated search programs, to the ones aided by set-like solvers. And now, starting from 2019, we see cryptanalysis methods aided by machine learning. So the idea is to mimic the differential-based key recovery attack by machine. Yeah. So we first train the machine to distinguish the reduced rounds with high probability differential from random ones. Means that as long as we know there's a high differential probability covering the entire portion of the attacked cipher, the machine should be able to detect it, yeah, by calculating the number of output differences satisfying this high probability differential. Yeah. And then to launch the key recovery attack utilizing such differentials. So these 2 steps were done by hand before, and now it can be mimicked by machine. Yeah. The first attempt was done by Guo at Crypto 2019 with application to Simon. And the second attempt was by my team. I guess you have heard the talk yesterday by Zhenzhen with all the details. So it was the first time achieving a complexity which is better than man-made attacks. So Simon was actually analyzed quite intensively since the proposal was made public in 2014, and it was actually unexpected that machine can actually do better than what we did, because we have accumulated decades of experience on differential-based key recovery attacks. Yeah. However, Okay, however, the limitation of machine learning is that it's limited by practical complexity, meaning that when the model gives you results, that means the model is working and give you results, and the result should be right. If it doesn't give you the results, there will be two possibilities. Either the model is wrong, or the model simply takes too long to output the results. Yeah. By our experiences so far, the application of machine learning based curve analysis is capable to apply to very short block size block ciphers. So Simon has the major targets we tried here are 32-bit block size, yeah, which is very small. Once it scales up to 64 or 128, the model becomes very, very slow and takes too much memory to do the training, and it won't be able to output us the results in practical time. Another difficulty is that there's currently no theoretical treatments of this machine learning based curve analysis. So for human, like for traditional differential curve analysis, we can do projection. Yeah? So if we can carry out the practical key recovery attack based on differential, then we can do a projection by adding up the number of rounds because we know adding this much of rounds, the differential probability will drop by this much. This is predictable, yeah? And the complexity of the final key recovery will also scale up accordingly. However, in machine learning, there's no such thing, okay? Because we have to ensure we get a distinguisher before we can do key recovery. And we can only guarantee us we get a distinguisher by the result, the practical result so far. Yeah. When the block size scale up or the number of rounds scale up, the machine is no longer able to distinguish the target and the random oracle. We are not able to tell whether this is due to our limited amount of resources or due to the fact that it becomes indistinguishable. Yeah. So a theoretical model to treat this machine learning is in urgent need, so that we can try to scale up the attacks to larger block sizes and larger number of rounds. In conclusion, so far, collision attacks of SHA-3 is up to 6 rounds. So there are lots of security margin left because the SHA-3 in total have 24 rounds. So we are only attacking 25%, leaving 75% as the security margin. So maybe Kangaroo 12 is a good idea because it has only 12 rounds, means it can be twice as fast as SHA-3, and still we have 50% security margin left. For AES, we can do up to 7 or 8 rounds in classical and quantum setting. It's still usable because we have 20–30% security margin. But in quantum setting, it becomes very risky to use AES in hashing mode because it has 128 bits block size, offering maximum 2 to the n/3, which is 2 to the 43 collision resistance in theory. Yeah. So even there's no attack, I guess very soon we'll be able to see brute force search on 128 bits collision. Yeah. So it's not advisable. So to resist quantum attacks, people should really think about block ciphers with larger block size, such as 256. Yeah. So what to expect from future developments of group analysis? We really want to have a deeper look at the core algorithms under the solver and machine learning. So, so for both, as I mentioned, for both solver-based and machine learning-based group analysis, the bottleneck is that we are limited by practical time, practical resources. And when the model doesn't output us anything, we don't know whether it is due to the model or due to the fact that it becomes infeasible to attack. Yeah. So we really want to figure out how to project this so that we can scale up our algorithms and the text to a larger space. Yeah. And another reason is to having this, it is possible for us to select according to the performance of the underlying solver or machine learning, the best strategy to model the attack. Yeah. So that you actually reduce the practical solving time. Yeah. Yeah, that's my thought. Thank you.
Any questions?
Thank you for the nice talk to the collision search on the hash function and the AS. My question is, you mentioned that the break quantum, I mean that the classical and the quantum setting, what's the difference? I mean that I interpret that when you search, you will use classical searching over global search. That is the difference. What is the difference?
Here.
Okay, that is you're using global search.
Yeah, global search.
So how do you assume that the complexity of global search? Just classical searching is very simple, right?
Yeah.
So how can you estimate the complexity of global search?
Yeah, so the current global search complexity is assumed to be the square root of the search space. Okay. So of course, I don't have a quantum computer. I cannot ensure it practically, but that's the everybody says.
Okay. Yeah. I can understand. That is a theoretical.
Yeah, that's theoretical. Yeah.
Okay. So, another question, maybe I can challenge later. Is it possible to break by quantum machine learning?
Quantum machine learning?
Yes.
Yes. Break what?
Maybe next.
Okay. So there are two things which is constraining us from using machine learning for group analysis. One is time, the other is memory. I think the most constrained resources is the memory so far, because to train a very large block cipher, especially with 64 or even 128 bits block ciphers, the amount of data increase exponentially. So it becomes impossible for the machine model to accommodate so many data in memory. Yeah. However, for time, I think we can use up a supercomputer to parallelize all the computations. Yeah. So yeah, in that sense, I think it's difficult, especially given that the quantum memory is much harder to achieve than classical memory. Yeah.
Thank you.
Any more questions? All right, let's thank the speaker again.